Welcome back. We're going to use this simulation involving a stunt bike to analyze projectile motion in both the horizontal and vertical directions. Now, currently we've got a top view of our stunt bike, and it's going to be moving from left to right on the screen, and we're going to discuss the motion in detail. I'm just going to simply hit go, and I want you to watch how the motorbike moves from left to right. Now you can see that the simulation drops a dot at prescribed lengths of time. Now I don't know what those times are, it doesn't matter, but let's say it's every 0.1 seconds it drops a dot. And you notice the dots are evenly spaced, suggesting that the motorbike is moving with a constant speed. Now let's reset it and step it across. Every 3 steps the motorcycle drops a dot. Now I'm going to slow down the simulation, and I want you to notice that the motorcycle is in fact moving with a constant speed from left to right. So right now that's full speed. Let's move it back to 0.28. Notice it's a nice steady speed from left to right. Now the simulation also allows us to look at some vectors. So I'm going to look at the velocity vector on this motorcycle from the top view. So remember, we're looking down on this motorcycle. And notice the velocity horizontally is 4.94 meters per second. Let's examine this vector as it moves left to right. Now hopefully you noticed, even as I step it through, it stays at 4.94 meters per second. So we've got a constant velocity to the right. And in terms of our kinematic equations, there's only really one formula that does not involve acceleration. Remember, constant velocity means your acceleration is 0. So really the only useful formula to describe this with our kinematic equations is d is equal to vt. Displacement is velocity times time. And since we're talking about a horizontal direction, we can simply say dx is vx times time. Now let's reset it, and I'm going to show you another view. Okay, so here we've got our motorcycle, and again I'll turn off our velocity for now. Here we've got our motorcycle hidden behind this little box, it looks like, and I'm going to hit go, and let's see what happens. It goes flying into the air. Now remember, I've slowed down the simulation so we can see what happens. But basically it's like throwing a ball straight into the air. So let me hit reset. I'll run it one more time. Motorcycle rises, comes to rest, changes direction, and comes back down. And if I step it through, you can see the dots are no longer evenly spaced. They get closer and closer together at the top, suggesting that there's an acceleration vertically that's constantly pushing this bike back to the ground. And we know from experience this acceleration is caused by the acceleration due to gravity. Negative 9.8. The force of gravity is always trying to get that motorcycle back to the ground. So it's slowing the motorcycle down on the way up, and once it changes direction, it's speeding it up on the way down. Let's look at our vectors. So you can see my initial velocity on that motorcycle is 4.94 meters per second, and when I hit go, you can see it shrinks, and then it gets more and more negative on the way down. Now that was quite fast, so let's reset it and step it through. So as it's rising, the velocity vertically gets smaller and smaller and smaller and smaller until it reaches a value of 0 at the peak, where it suddenly changes direction, and now it gets bigger and bigger and bigger in the negative until it's back to its original value when it hits the ground. Now because we have an accelerated motion in this direction, we have a choice of 3 kinematic equations, or at least 3 kinematic equations. D is v initial times time plus 1/2 at squared. V final squared is v initial squared plus 2ad. And v final is v initial plus at. Basically, any equation with acceleration is valid for this motion because it is in fact accelerating. And in all examples, the acceleration is down. It's pushing the object back to the earth, and it's always negative 9.8. So we have 3 choices of equations for this particular motion, and our acceleration is always due to gravity. Now if this was on the moon, of course, negative 9.8 would be negative 1.6 for the moon's acceleration due to gravity. Now the thing is, this is actually projectile motion. So let me hit reset and show you exactly what happened. This is actually the front view of our motorcycle. Originally we had the top view of our motorcycle, but if I look at it from the side, this is the exact same motion that we just witnessed from the side view. Here's my x velocity, there's my y velocity. When we were looking at it from the front, we were unaware of that it actually had a horizontal velocity. When we were looking at it from the top, we were unaware that it actually had a vertical velocity. And the point I'm trying to make is that these two directions are completely independent of one another. You can study the x direction independently of the y, and really the only thing that links those two together is time. The time it takes for the motorcycle to travel from left to its final destination on the right, it's exactly the same as the time it takes for the motorcycle to reach its maximum value and fall back down to the ground. Now I'm going to hit start or go, and we'll see what the actual motion of that motorcycle looked like. As expected, there's our projectile motion, and if I step it through, you notice the y velocity shrinks just like we witnessed before, and its associated equations are those three equations that we discussed. The x velocity stays constant, and its associated equation is simply d is equal to vt. That's really our only choice. And in the end, it hits our target, or at least tries to hit our target on the far right. Now what I showed you here was a type 2 projectile, but what we're really trying to illustrate is our choices of equations. Vertically, we've got our three choices of equations. As long as all the variables we use in this column are vertical variables, in other words, displacement in the y, v initial in the y only, v final in the y, ay, everything has to be parallel to each other in this direction, so all these vectors must be vertical. In our x direction, in the other column, everything once again has to be parallel, so we would have to choose dx and vx. And remember, the link for the two sides of the equation is time. So once you know time using either the left side or the right side, you can continue on and solve for everything you need.